have to talk about unless one gets into engineering details is pretty simple anyway. And the crux of it is an idea I've been thinking about for a number of years. I mean, the high level motivation was introduced by Rachel in the start of this workshop, which is, I mean, we've gone a long way in deep learning, for example, by optimizing hardware better and better for the sorts of neural learning and inference algorithms that we have there. It started out with using GPUs tuned for graphics, and then you have all these architectures tuned for neural stuff. So when you're looking at other AI architectures and algorithms, such as OpenCog Hyperon, for example, or hypervectors, as we've just heard, I mean, then you have the question whether some custom form of hardware can accelerate that in the same way. And the key operation that you need to optimize to make OpenCog-based AI fast is pattern matching on metagraphs. And this is characteristic of most software systems that are engaged with manipulating large graphs. I mean, almost all the workload there is reading and writing to the graph rather than doing number crunching or something. Whereas in computer graphics or in deep neural net applications, most of the work is in multiplying matrices to update the weights on a network. It's different. In graph-based systems, you got this big graph in RAM. You usually like doing a pattern match of some sort across the graph, grabbing some bits and pieces of graph out, combining them together, and then putting some more stuff back in the graph. And putting it back in the graph is not usually that expensive if you know where to put it, right? But finding this stuff in the graph is expensive. So I mean, we have the whole OpenCog Hyperon architecture, which I talked about a bit in the workshop 3 days ago. I mean, you have atom space containing nodes and links. You have a distributed atom space. You can have a neural space. You have the meta language, which can compile into Rolang. You can have large language models connected. But in the end, whether through meta directly or through meta compiled to Rolang, as well as looking at distributed stuff, he's doing a lot of pattern matches against atom space based in RAM, right? And I mean, Rolang optimizes this in some ways. By compiling meta to Rolang, you can make better use of hyperthreading and so forth. But of course, there's only so many hyperthreads, right? So I mean, if you had a chip design that's specialized for Metagraph pattern matching, then of course life becomes much easier and things can go much faster. Now, I looked at GraphCore and some other graph processing chips, and unsurprisingly, it comes out hardware is very specialized. So, I mean, GraphCore, when you look at it, is very optimized for things like graph convolutional networks, where you're mostly concerned with iteratively updating floating point weights on lengths of a graph or weights associated with nodes of a graph. And if you're mostly updating discrete stuff associated with nodes and links in the graph, then a lot of the floating point firepower on a graph core is wasted, and by the same token, you're not using that part of the chip for what you really need. Now there are discrete operations. I mean, there are floating point operations, of course, in OpenCog, so it's not totally wasted. It depends what you're doing, but an awful lot of what we're doing is more discrete. And given this is a fairly heterogeneous architecture, there's a lot of aspects. So if you have a neural space, like a neural atom space, you might want a graph core for that. You might want a traditional deep learning chip, right? And you can also take nodes and links in atom space and embed them. I mean, we've embedded them previously into, say, 50-dimensional vectors. You could also embed them into hypervectors, right? So you can embed each node or link in the atom space into a hypervector. Then certain sorts of searches and manipulations will be done very well on these hypervector embeddings, and for that, that the Simuli hypervector chip is one option, and there's other specialized chip architectures out there that are also probably good for these hypervector operations. But before I had met Rachel and found out what she's doing, I started to think about what could you do in terms of a specialized chip architecture for Metagraph pattern matching. And I don't know too much about hardware. I have a bunch of friends who know more about hardware. So pretty much I started going through the literature to see what specialized chips there were for graph processing in various ways. Started to think about how would you kind of hack that to do with Metagraph pattern matching, then bounce the ideas off a few people from the hardware space. So among the various papers I was looking at, there's architectures like this, and there are many architectures like this. This paper is one example, which is better in some ways and worse than others. But this is processing and memory architecture for processing large graphs. And pretty much what they do here, they take these processor cubes, which you can just buy, and each processor cube has like eight layers of memory, and it has some processor and a controller associated with it. And what they do here, they lay out these cubes in a square grid, and pretty much they take the graph and partition it. So they're dealing with the case where the graph doesn't change too much, right? They take the graph and partition it among the squares in this grid, right? And I mean that leads to very obvious implementations of many graph algorithms, right? So you're searching for something in a graph, well, just search separately in the part of the graph in each grid, and then collate the results together. Now it's not quite as simple as that. I mean, you'll have links between a node in one cell and a node in another cell, which you have to deal with. And periodically, which is a quite expensive operation, you want to be able to move stuff from one cell to the other cell. But as the hardware works, pretty much you have to freeze processing in order to move stuff between one cell in the grid to another. So you're not able to reorganize the graph among the grid cells in real time. But so they give nice results from simulations of this. I'm not sure they ever actually built this particular chip. There's a bunch of other architectures out there, but when you dig into it, similar things with some changes can be done for Metagraph pattern matching. So Rachel and I worked out some of these particulars together and bounced them off various people from the hardware space. No one found any obvious problems with sort of adapting these graph chip designs to Metagraph pattern matching. Pattern matching is a different algorithm than the ones that they were considering. But the basic architecture is in you have these hybrid memory cubes, which have processor and memory in them. I mean, inside each cube, you have a bunch of different little memory vaults, and then you have some additional RAM. The vaults each have logic units and a local memory cache. So there's some parallelism within each cube. But the nice thing is you can just buy these cubes from a supplier, right? So then, I mean, creating this overall chip from these cubes, I mean, there's still care. It's still a thing to do. But the hard part is really in those cubes, which manufacturers are already doing, right? Then you have a global RAM that all the cubes have access to, where obviously the access there is slower than to the memory cache inside each cube that you have. And so then the logic units, which are inside each vault, right? The logic units, you're dealing with both discrete and floating point processing units there. And at this level is where things start to operate differently than a graph core, because the graph core is just focusing on floating point operations when you get down to this level. Whereas we do want floating point, but we need fast discrete processing at this level, and you can tune the particulars of the discrete processing unit based on what you need to do pattern matching effectively on the graph, which gets more and more detailed. Now the memory cache also is interesting because you have the opportunity to put sort of ECAN or hot field net type activation spreading stuff like at the hardware level. So there are many interesting parallels between this and the distributed atom space, actually, because with the distributed atom space, I mean, you have a bunch of different machines that have parts of the atom space memory graph, right? And then moving atoms from one machine to another is much more expensive than rearranging them within RAM of some machine. You also have a persistent store, and then you need to do some clever caching to figure out what comes out of the persistent store and stays in RAM for a while, right? So here you have a similar set of issues. You want to determine what stays in the memory cache, which is in a given vault, which is inside a given cube. Now, the difference, of course, is here, I mean, you don't have as much memory to work with because everything's being put on the hardware. On the other hand, activation spreading type heuristics are not very expensive, right? So putting activation spreading sort of heuristics for determining what should be in the cache here is an interesting infusion of some simple but potentially powerful AI down to the hardware level in a way that's different than what is done in the graph chip that I mentioned. Because if you're just doing sort of standard graph algorithms, doing activation spreading for your memory cache is not necessarily going to do what you want, right? Whereas if you're doing this sort of semantic pattern matching on an atom space representing the mind of an AI system, often using activation spreading of various sorts for your cache is what you want. So here, with stuff like the cache management policy is one place that you're like fine-tuning the chip, not just for pattern matching, but for this sorts of pattern matching that you wind up doing in building a cognitive system. So, for example, if you were trying to use this as a backend for a Haskell compiler or something, the sorts of optimization you do for the pattern matching inside Haskell are not necessarily the same as the sorts of optimization you do for the pattern matching inside a cognitive system, because the cache management policy would not be the same. So you have an overall pipeline then going from the OpenCog Hyperon software application finally down to these memory cubes, and the double mesh I'll explain in a moment. But I mean, you need a special compiler that takes the pattern matching in the atom space and compiles it into something that will run on the hardware. And you need something to partition the graph in the right way. And if you have a graph which is always changing because you're doing like hardcore code self-modification or something, I mean, then you just don't put it on hardware, right? I mean, the case ideal for this is like you've parsed all the knowledge in Wikipedia or something, or you've crunched a bunch of data sets, or you've just learned some body of procedures for dealing with a certain class of situations, which you know is really good for dealing with those situations, right? Then it's not that you can never change that, but changing those nodes and links is not the main thing you're doing. You're more often just using it to do something. So if that's the case, put it down on hardware, then you can do pattern matching on it quite efficiently. So It's a little bit like the distinction between model learning and model inference in the neural net world, but it's not quite as rigid. And one thing we figured out after a while is that moving nodes from one cube to another is a quite costly operation, and you actually have to freeze everything happening to update the memory everywhere in an effective way. So what I think you end up doing is, if you always want things to be operational, like you take your current memory grid, copy it to a second memory grid, then freeze that guy and reroute everything on that guy, and then when you're not doing any rerouting, you just have two copies, which is, if you're accessing the thing a lot, is fine. You can rapidly access the two copies. If you need to reroute things because the graph changed, so it's no longer optimal to have the nodes grouped together that were grouped together, then you just freeze one of the grids and reroute on there, but you still have access to the other one. And I mean, it's all not easy. I mean, there's a lot of programming to do, but still, you're sort of putting the Lego blocks of these cubes together. So it's not incredibly hard compared to many things in chip design. Yeah, Adam.
Yeah. Why do you have to copy it instead of being able to route the traffic to one mesh or another mesh?
Well, if you have updated one mesh because it's better, why do you want to leave the other one old, though?
No, like I mean, you routing it to one that has already updated while you're updating this one.
Well, that's true, but then you don't want to redo all the work to update the other one.
Oh, right.
Just copy the updated version over.
So it's easier to copy than to update.
Yeah. I mean, because the hard parts. I mean, the hard part is just sending stuff between the cubes. It's not any harder to send stuff here than to send stuff between the cubes, and then you're saving just the computational operations done. So, I mean, we've designed this, and we've got to go the same route as with the other hardware that's discussed. I mean, we've got to go to FPGA, and then once you have it running on FPGA, there's many shops in Shenzhen and elsewhere that will deal with the next step for you. But going to, probably we will do a step before that, and I'm talking to people who are good at doing simulations of hardware. So then we'll probably do sort of a software simulation just to tune all the parameters of everything, because there's nice chip simulation toolkits in Rust, and the atom space for Hyperon itself is in Rust. So I think we can make a nice software simulation of all this and connect it to the actual Hyperon pattern matcher. Then that will let us tune all the quantitative parameters of everything and the specific logic operations before feeding it to an FPGA guy. So we bounce this across a couple experienced hardware engineers who seemed happy with it. But exactly how much speed up you'll get, I mean, we just sort of have to run simulations to tell, but it will also depend on sort of the size of the patterns and the nature of the atom space. So trying to do sort of rough back of the envelope calculations, it seemed to me that if you had, say, Wikipedia parsed into logic, right? And then you're doing pattern matches of the sort that you have for natural language query processing, which is only one sort of thing to do. But it seems that then a vast majority of the time, you're doing like a small lookup, which is going to be within the part of the graph stored in one cube. And of course, you can do fancy things like nodes that are at the edge between the two. You can just store copies of them in both. So if you have small patterns, there's very small odds that they're gonna span between the two of them. So if you're dealing with that sort of case where it's a pretty static graph, like the knowledge in Wikipedia, and it's a small pattern like you get from a typical natural language query, then pretty much the speed up should just be proportional to the number of cubes in the lattice, because you're just searching everywhere in parallel and then taking the best answer you got and delivering it, right? And then other cases where the graph is a little bit dynamic or the patterns are bigger, depends more heavily on the particular statistics of the graph, right? So I think what Rachel and I have been scheming is then like an AGI board where you have deep neural net chip, hypervector chip, OpenCog pattern matching chip, CPU, and you're wiring these together with sort of fast processor to processor interconnect and have some shared memory among all these things. And it seems like, hypothetically, if all goes well, a chip like this can do for Hyperon type AGI something similar to what GPUs did for matrix multiplication based AI. Now we don't have what they had, which is computer graphics as a huge economic driving factor to lead toward those chips, right? I mean, but we're building something specifically for our AI system. But I would say there's a lot of other applications out there where you have large graphs and want to pattern match again. So I mean, every social network has that problem. I mean, the intelligence agencies, while not my favorite customers in every respect, I mean, they have that problem also, right? So while the motivating factor here is Hyperon, I think there would be many other applications where pattern matching against a large, slowly changing graph needs to be sped up, right? I mean, and Cray has graph processing supercomputers also, so there's various approaches out there, but it seems like doing this sort of MIMD parallel processor in RAM tuned for pattern matching has not been done before on graphs, let alone metagraphs. And that's it, relatively short and sweet.
That's great. Thank you very much, Ben. Any questions from the room?
One question for the graphs. Were you considering storing them as triples or storing them as vectors in the hyperdimensional representation?
The hyperdimensional representation.
In the vector representation, were you going to be using them as
separate things? So I think I think maybe
you're asking about hypervector embeddings?
Yeah.
I mean, for that, so first of all, this particular chip design is not based on hypervector embeddings. I mean, you could explore that, but that would be a direction we haven't gone, right? Because if you're making a hyper embedding of the nodes and links in the graph, in the chip architecture in the board architecture we're looking at, the most natural thing would be to then do the work on those hypervectors in Rachel's hypervector chip or some other variant there. I mean, hypothetically, you could try to take the hypervector chip and the pattern matching chip and like make a version of the hypervector chip that's layered on top of the pattern matching chip. But we haven't looked at that yet, and I'm not sure if it makes sense. So in this chip design that I just outlined, you're not using a hypervector representation within each memory cube. You're using some other efficient graph representation. Adam wants to say something.
Yeah. So two intertwined questions. One question is, you know that like many natural graphs follow this Zipf distribution, right? This power law distribution. And when I look at the chip, yeah, I see like squares and like maybe at most cubes. And to me, there's like a topology mismatch where you want to break up like large nodes. Like you have a few very large nodes, and they need to be somehow distributed over this mesh. And then the intertwined question is that in a graph, distance is really weird, right? And it's very hard to project it into 2D or even like 2D times 3D.
Well, so you can make multiple copies of the same node. So if you're doing natural language or something like it, I mean, a node representing a function word like of or something. So you could have a copy of that node in multiple squares, and in that way, this is very similar to distributed atom space, right? Because you will want to do the same thing in the distributed atom space. So if you're looking at like Zipf's law with natural language, there's not. I mean, precisely because of that law, there's not that many nodes that you would need to copy and put among all the different cubes, and everything in the long tail you don't have to copy.
So you're flattening the distribution a bit by
a bit, but
yeah.
but even it's going to be more like 1/10 of the nodes in each cube are replicated. It's not going to be like 80% or something.
And then the intertwined question, just to repeat, was like, how do you deal with the locality? Is it also by the copying? Like, is that like the same solution for both questions?
Yeah, it is, right? Yeah. At least I can't think of a better solution at the moment. Yeah. And the elegant thing there is that all these things occur in a distributed atom space also, right? So, yes. I mean, with this design, because it's all sort of partitioning based, and you're dealing with the idea that processing within one partition is much cheaper than going between them, and rerouting is costly. So that the nature of the constraints is kind of the same on distributed atom space level as in this sort of MEMD parallel thing. And then the quantitative parameters are all going to be different. So you need some tuning, but the conceptual approach is kind of similar, which is elegant.
The thing I did not fully understand is the expressiveness of the possible or the set of possible rewirings. So, because you showed two graphs, one where we had just cubes, like on a matrix of cube, and one where cubes were layered, and so I don't understand which one is the physical one, which one is the abstract one is, and
everything shown there was physical.
Okay.
Or was a pictorial depiction of things that are supposed to be physical once we build them. But it's also all physical because we're in the physical world.
What are the constraints? What are the constraints in terms of wiring a cube to another cube?
I don't know, to be honest. I mean it's the same as in the paper I referenced and others, but I mean, of course, the quantitative, I mean, the speed of transmitting stuff between one cube and another is it's much slower than propagating stuff within a single cube. Right. But I don't actually remember the exact proportion.
I mean, you have a cube here, you have a cube there. You're not going to be able to connect them directly. Right?
That doesn't make such a big difference. I mean, but cube to cube is much more expensive than within a cube.
Right. Yeah. This is clear. Okay, because you were talking about, okay, we're going to copy from different meshes so that we can rewire, reconfigure, and I'll tell you what that means.
Well, to rearrange. The point is that you've partitioned a graph, right? And the obviously an atom space graph isn't a partitioned graph, right? Mm-hmm. So you're partitioning the graph in some approximate way among these different cells, right. And to count for things that logically should live in more than one partition cell, then you're making copies of some of the nodes, putting them in multiple graphs. Yeah. But if you have a lot of reasoning going on, then the graph itself is changing in topology, right? So then at a certain point, after the graph has changed in topology enough, then you're going to want to repartition, right? And the point is repartitioning the graph is expensive operation.
But isn't that, in that context, isn't that when you're not changing the physical connections between the cubes, isn't that just
No, but you're changing
copying
what,
stuff
you're changing
around?
what goes in the memory of each cube. No? And
Right.
you're just like potentially refreshing the whole memory of each cube.
Yeah,
right?
and so that's the
Yes.
operation that requires pausing.
Yeah. That's right. Yeah.